On July 1, 2025, the Atlas telescope detected a single point of light moving too fast, too steadily, and far too unlike any comet we've ever seen. Within hours, astronomers around the world were talking about one object. The first calculations were clear. Its trajectory was hyperbolic, which means only one thing. It came from outside our solar system, and that's where the debate began. Some claimed it was just an interstellar comet. Others argued that its characteristics didn't fit any known physical model. But almost everyone agreed on one point. 3I Atlas does not behave predictably. None of the familiar explanations worked. Not for its shifting brightness, not for the subtle deviations in its trajectory, and not for the conflicting measurements reported by different observatories. The object turned out to be both unusually bright and strangely quiet. Too light to be a comet, too unstable to be an asteroid. It appeared suddenly and broke every expectation so completely that the discussions around it still haven't faded. To understand what we were looking at, a coincidence, a natural phenomenon, or something that demands an entirely different vocabulary, we asked an artificial intelligence system to examine 3I Atlas as raw data, not as a comet, not as an astronomical oddity, but as an equation that might contain a hidden meaning. And its analysis didn't just explain how the object behaves. It led to a version of how 3I Atlas may have come to exist at all. Interstellar objects are the rarest visitors ever to pass through our solar system. Throughout the entire history of astronomical observations, we've managed to detect only two of them, ʻOumuamua and 2I Borisov. They arrived quickly, left even faster, and raised more questions than they answered. In theory, these wandering drifters should cross our path far more often. But in reality, years, sometimes whole centuries, separate each appearance. We know almost nothing about them, where they originate, why they emerge suddenly, and what they carry with them from distant star systems. That's why 3I Atlas became an event on its own, even before the first anomalies were discovered. Every interstellar object is a one-of-a-kind opportunity to look beyond the borders of our own solar system. 3I Atlas drew attention immediately because it didn't fit into any category we know. It's too light to be an asteroid, yet too active to behave like a comet. Its spectra produced noticeably different results on different days, and the changes in its brightness didn't match any familiar mechanism of reflection or evaporation. But the real challenge wasn't the anomalies themselves. It was the fact that different telescopes saw the object differently. The observations refused to form a single, consistent picture. Some parameters lined up, others contradicted each other. As if 3I Atlas showed a different face depending on who was looking. At that point, traditional methods stopped working. To understand an object that can't be studied twice, and that leaves behind nothing but fragments of disconnected measurements, we needed a tool capable of comparing everything at once. Its trajectory, spectra, brightness, coma behavior, changes in velocity, and its interaction with the solar wind. That's why we turned to artificial intelligence. It doesn't require complete observations, only recurring patterns that appear across different data sets. We didn't ask the AI to label 3I Atlas. We asked it something else. Does its behavior look natural? Or are we dealing with something of a different order entirely? And what the AI uncovered will show just how far this mystery strays from the behavior of an ordinary comet. Until recently, interstellar objects were more of a theoretical idea than an observable reality. Scientists assumed they should enter the solar system regularly. Fragments of distant planetary systems ejected into interstellar space. But until 2017, we hadn't seen a single one. That changed with ʻOumuamua. It was moving too fast to be held by the sun's gravity, and its trajectory made one thing unmistakably clear. It came from beyond our system. ʻOumuamua was the first real proof that interstellar objects exist, but it was also deeply unusual. No coma, no tail, a flattened, elongated shape, and a faint, unexplained acceleration. 2 years later came 2I Borisov, the complete opposite. A true icy comet, with a bright, active coma and perfectly understandable behavior. Astronomers called it the first normal interstellar object. It seemed we now had two categories, the anomalous and the ordinary. But then 3I Atlas arrived and broke that simple division. It resembles ʻOumuamua in some ways, and contradicts it in others. It resembles Borisov, and contradicts it too. It has a coma, but it's unstable. Its spectra look comet-like, but only sometimes. Its motion resembles something natural, yet includes deviations that are difficult to explain. Interstellar objects are rare on their own. But even rarer are those that don't fit into any existing model. And here's the real problem. We can't fly to 3I Atlas, take a sample, or see it up close. All we have is its trajectory, its brightness, its spectra, its velocity, and how all these parameters change over time. For a comet or an asteroid, this would be enough. But for an interstellar wanderer that breaks familiar patterns, it's nowhere near sufficient. That's why the next step in our investigation is to pinpoint exactly where the anomaly begins, and to compare those deviations to what we consider normal for objects arriving from another star system. When we compare 3I Atlas to the only two interstellar objects we've ever seen before, one thing becomes clear. Its strangeness isn't a single feature. It's a chain of details that simply don't appear together in natural comets. The first anomaly is its motion. Interstellar objects usually follow clean, predictable hyperbolic paths, but 3I Atlas seems to pulse along its trajectory. Tiny accelerations followed by tiny slowdowns, appearing exactly at moments when the path should be perfectly smooth. None of the familiar explanations fit. Not the gravity of nearby planets, not solar radiation pressure, not thermal effects. The second anomaly is brightness. A comet brightens gradually as it approaches the sun, but 3I Atlas jumps, brighter, dimmer, brighter again, with no link to distance. The third anomaly is the coma. In a normal comet, the coma is fed steadily by evaporating ice, but with 3I Atlas, the coma appears and fades as if its source turns on and off. And that raises the question of internal structure. Indirect calculations suggest that for its brightness, the object is too light, with a density far lower than expected for a rocky, icy body. And then there's the strangest part of all, its reaction to the sun. Instead of becoming more active as it gets closer, 3I Atlas sometimes becomes quieter, as if its behavior isn't driven by heating the way a comet's behavior should be. To understand what's random and what's a real pattern, we asked artificial intelligence to compare the parameters of 3I Atlas with thousands of comets studied over the past decades. The AI generated combinations, shuffled datasets, and searched for recurring signatures, and eventually found that several properties of 3I Atlas almost never appear together in natural objects. Each individual anomaly can be found in ordinary comets, but their combination, the velocity dynamics, the brightness jumps, the unstable coma, the unusual density, and the anomalous reaction to heating, is nearly absent from natural scenarios. This isn't proof, but it isn't coincidence either. It's the point where the real investigation begins. A trajectory is one of the most reliable ways to understand the nature of a cosmic object. A comet can change its brightness or activity, but its path always obeys physics. No exceptions. With 3I Atlas, that rule began to break. At first, its trajectory looked normal, a standard hyperbola of an interstellar visitor. But as the calculations were refined, the line started behaving in a way it shouldn't. Microscopic deviations appeared, too small to see with the naked eye, yet stable enough not to be dismissed as noise. And most importantly, these deviations appeared exactly in the parts of the orbit where nothing was supposed to change. If the sun were responsible, the deviations would point outward. If it were the gravity of the planets, we'd see characteristic bends. If it were solar wind, The speed changes would match its fluctuations. But none of these explanations accounts for the behavior of 3I Atlas. Not fully. The deviations look as if the object is receiving tiny, barely detectable impulses in a direction that doesn't match solar pressure or gravity. That's where we turn to artificial intelligence. We ask the algorithm to build a dynamic model of 3I Atlas, not from a single set of observations, but from all available data at once. Daytime and nighttime measurements, different observatories, different phases of its approach to the sun. The AI compared how the speed changed with even the smallest variations in distance, how the object reacted to heating, and whether the deviations matched anything that could be called a natural response. And that's where the key result appeared. According to the AI's calculations, the velocity of 3I Atlas shifted in a way that suggested the object was receiving a faint impulse from a direction that didn't align with solar pressure or gravitational forces. These shifts are far too small to make bold claims, but far too consistent to dismiss as coincidence. It doesn't mean the object is controlled. It doesn't imply intent or directed motion. But it raises a question. If the impulse doesn't come from gravity, doesn't come from evaporating ice, and doesn't come from solar wind, then what produces it? We don't have that answer yet. But we can say this. The trajectory of 3I Atlas behaves as if there is another factor in play, one we haven't identified. If a trajectory tells us how an object behaves in space, its spectrum and light reveal what it's made of and what's happening on its surface. For interstellar objects, this is the most important source of information we have. We can't fly to them. We can't examine their structure up close. All we can do is analyze the light they reflect and emit. With 3I Atlas, its spectra became one of the central mysteries. On some days, it looked like a typical comet. Clear signatures of volatile compounds, familiar lines from evaporating ice. But on other days, the spectrum shifted abruptly. New lines appeared. Lines that shouldn't form or disappear so quickly in a natural icy body. Several observatories noticed something else. Small patches of increased brightness on the surface of 3I Atlas. Tiny points that flared for a moment and then vanished. In scientific reports, these are cautiously labeled localized zones of energetic activity. They don't resemble gas jets, which expand smoothly and gradually. These flashes are brief, precise, almost impulsive, as if the source switches on and off. These moments led researchers to suspect that the surface of 3I Atlas might be far from uniform. Some regions reflect light differently. Others seem to respond to heating unevenly or with a delay. We asked artificial intelligence to analyze these spectral variations not one by one, but as a sequence of events. The AI identified phases where the flickering bright points and the changes in spectral composition shifted in sync. And in several of those phases, it detected short bursts of light without the telltale signs of evaporating ice. In other words, we see a flash, but not the gas or dust that should accompany it in a normal comet. What could that mean? There are several natural explanations. An uneven internal structure, unstable surface patches, large fractures that release volatiles under pressure. But the AI pointed out something different. These flashes don't occur randomly. They appear at specific phases of 3I Atlas's position relative to the sun, as if the object has regions that become active only under a certain angle of illumination and then fade again. For comets, this behavior is extremely rare and almost never localized. Cometary activity usually spreads across large areas of the surface. The AI built a model to map the distribution of these flashes and found a pattern. They cluster within a narrow band of the object's longitude. Put simply, they appear as if they come from one side. This doesn't prove anything unusual, but it raises a new and important question. Why does that specific side produce energy bursts that aren't accompanied by the usual gas emissions? We don't have the answer yet, but this feature will become crucial in the next stage of the investigation. When 3I Atlas entered the solar system, many researchers immediately recalled the object that became the first major interstellar mystery in modern astronomy, ʻOumuamua. Both objects came from beyond our system. Both passed through quickly, leaving no chance for close-up study. And both behaved in ways that ordinary comets simply do not. So we asked artificial intelligence to compare the full dataset of 3I Atlas with the complete archive of observations of ʻOumuamua. Not to chase a sensational claim, but to answer a simple question: do interstellar objects share the same anomalies, or was ʻOumuamua a one-time exception? The AI analyzed trajectories, velocity changes, brightness variations, coma behavior, and spectral signatures, searching for overlaps. And it found 3 features that both objects share, features that almost never appear together in natural celestial bodies. The first shared feature: microscopic accelerations not explained by gravity. ʻOumuamua exhibited them faintly. 3I Atlas shows them more clearly. But the pattern, the logic behind when they appear, is strikingly similar. The second, unstable brightness. Both objects displayed abrupt jumps in reflected light with no obvious link to their distance from the sun. Comets can behave this way, but rarely and almost never with such sharp fluctuations. The third, uneven surface activity. For ʻOumuamua, this appeared as the absence of a classical coma. For 3I Atlas, it appears as localized flashes and an unpredictable coma. Different forms, but the same underlying idea. The surface responds to heating in a way we don't typically see. Each of these anomalies can be explained naturally on its own, but the combination, across 2 completely different objects from different systems observed years apart, raises a new question. If an anomaly repeats, is it still an anomaly? Or is it a pattern? And that observation from the AI becomes the bridge to the next part of our investigation, where we ask whether 3I Atlas can truly be explained by known physics alone, or whether its behavior points to something of an entirely different order. After analyzing every anomaly, the trajectory, the brightness variations, the coma behavior, the spectral flashes, and after comparing 3I Atlas to ʻOumuamua, we face the central question: what exactly are we looking at? A normal comet? An unusual fragment of interstellar debris? Or something that falls outside natural scenarios? We asked the artificial intelligence not to search for dramatic answers, but to build a strict model of 3I Atlas's origin based solely on what the data actually supports. The algorithm was given a task: simulate every plausible scenario and keep only the ones that explain the largest number of observations with the fewest assumptions. The AI began with the basics. Hypothesis 1, a natural comet. The most straightforward, textbook explanation. Interstellar comets do exist. They can be porous, unstable, and sometimes behave unpredictably. The AI checked, can an ordinary comet produce all these features at once? Brightness jumps, possible. Unstable coma, also possible. Low density, happens. But once microscopic accelerations and the object's strange response to solar heating were added to the model, the hypothesis began to break apart. For a natural comet to behave consistently this unusually, it would require physical conditions that have never been observed in any body of the solar system. The AI kept this version, but marked it as unlikely in its current configuration. Hypothesis 2, a gravitationally disrupted interstellar fragment. Another possibility, 3I Atlas could be a piece of a larger body torn apart by tidal forces near a massive star or giant planet in another system. Such fragments can be extremely porous, irregular, and chaotic in structure. The AI tested the model. Some traits fit better: low density, uneven surface, sporadic bursts of activity. But the same problem returned: the trajectory. Disrupted objects behave chaotically, but chaos is random. 3I Atlas's deviations were not. They repeated in the same phases of its journey. That's not residual chaos. That looks like a response. The AI kept this hypothesis below the first. Hypothesis 3, a fragment of technological origin. The algorithm was required to test this scenario, not as a sensational claim, but as a mathematical model where impulses and deviations could arise not from natural processes, but from the structure of the object itself. The model doesn't assume intention or an active mechanism. It describes a scenario where some properties result from internal features, residual energy, uneven surfaces, or a mechanism that once produced weak impulses but no longer functions in a recognizable way. The AI noted that several parameters of 3I Atlas, the stability of microscopic accelerations, the localized flashes, and the unusual reaction to solar heating, fit this model surprisingly well, not as proof, but as mathematical compatibility, AI's version of the origin of 3I Atlas. When the algorithm combined all anomalies of 3I Atlas at once, it produced a single scenario that explained more observed features than any other. According to this model, 3I Atlas may be a fragment of a larger object that, millions of years ago, passed too close to its parent star or a giant planet. Tidal forces tore it apart, leaving dense, porous, irregular fragments. Some of these fragments could have preserved within them traces of a structure or remnants of activity that no longer operate, but still influence behavior in subtle ways. A fragment like this might retain faint directional impulses, point-like flashes, unstable brightness, an unusual response to heating, and trajectory deviations repeating in the same phases. The AI does not claim artificial origin, but its model shows that part of 3I Atlas's behavior aligns with what could be remnants of once controlled motion or long-faded structural activity. Not a spacecraft, not a functioning mechanism, but a fragment that may have outlived its creator by millions of years. When the AI finished comparing all models, the scenario of an ancient disrupted object turned out to be the one that explained the greatest number of features at once. But to turn that scenario not into an image, but into a mathematical result, the algorithm combined every parameter of 3I Atlas into a single final estimate. It took into account the stability of microscopic accelerations, the repeated deviations in its trajectory, the localized flashes, its reaction to heating, unstable brightness, unusually low density, irregular coma behavior, specific spectral lines, and, most importantly, the combination of these traits, a combination almost never found together in natural objects. All of these parameters formed a profile that matches comets and disrupted bodies partially, but matches no natural object we have ever observed completely. That is why the AI's final conclusion is not a statement about origin, but a probability. Probability of an artificial origin for 3I Atlas, 34%. Not a claim, not a revelation. Just the numerical distance between the object's behavior and what we classify as natural, 34%. Small enough not to draw conclusions, large enough not to ignore. Because if even a fraction of that probability reflects reality, then 3I Atlas is not an isolated case. It is a trace, a remnant of something that once existed, was torn apart, and continues to move through the galaxy far longer than our species has existed. And perhaps we are not the only ones in this galaxy who watch the traces left behind by others.